In this video, I'll be going over the problems to the Google Code Jam qualification round for 2020. And instead of like most other videos where I try to solve these problems as fast as I can while only giving brief explanations, I'll be, as I think through the problems and try to solve these, I'll be giving more of what I'm thinking and how I'm approaching the problem. So hopefully that'll be helpful to anyone who's watching this. Okay, let's start. So we need to compute k, which is the trace, which is the sum of the elements on the main diagonal, and then we need to do r, and then compute r, and then we need to compute c. And r and c are pretty similar. These two have similar logic. I'll go over computing k first. So for computing k, it should be pretty simple. I'll just input the matrix first. So now we're trying to compute k, and we just add up all elements on the main diagonal, which is just row 1, column 1, row 2, column 2, and so on. And this is pretty straightforward with a single for loop. Okay, and then what we'll do is to calculate r, we'll loop through each row, and then for each row, we can keep a set. Yeah, we can use a set to see if we have any duplicate elements in the row. So this for loop loops through all rows, and then for each row, we'll start with an empty set, and then each set, and we'll just loop through all the elements in the row, and we'll add elements to the set. And in order to check for duplicates, basically, before inserting the element, we need to check if the element is already inside the set. So I'll have a Boolean variable here, duplicate, and then before we insert the element, if we can already find it, then that means there's a duplicate. And finally, if there is no duplicate, then we'll just add 1 to r. Then the logic for finding no columns is pretty much the same. So I'll just copy this over and make a few changes. And this should be it. And lastly, just output k, r, and c. And let's see if this works. Oh, okay, I think I messed it up. Like, I'm supposed to count the number of rows and columns with duplicates, not without. Yeah, now it works. So now I'll just submit this and hopefully it'll pass. And okay, cool. Is there only one test set? Oh, I see. Okay, cool. So now we're on to the second problem. Okay, so at the start, we should process all of the, I feel like we need to process all the digits from left to right. And we basically just basically modify the string as we go. So in other words, so for example 101, at the very start, the nesting depth is 0 because we don't have any opening parentheses before it. But then we need and when we process the first character, we need a nesting depth of 1. So since the current depth is 0, to make it 1, we just add an opening parentheses here to make it to make it 1. And then we process the next character. Our current depth is 1 and we want to make it 0. So we just, by adding a closing parentheses, we can make the depth 0. And we move on to the next character, we can do the same thing. And then lastly, at the end, since all the parentheses should be matched, we actually need to add a hidden 0 in the end. We need to pretend like there's a 0 in the end. And so then after we add a 0 in the end, if we repeat the process and we make sure that the depth becomes 0, then we will obtain a valid string that will obtain a final solution. Yeah, and this also extends for like more digits. So if we have 2, we have something like 2, 3, 1. What we'll do is we start at 0, and then when we process the 2, we add 2 in the front, and then when we process the 3, we already have 2 in the front, so we just need to add 1 in the beginning. And then when we process the 1, we have a depth of 3, and we need to subtract 2, so we add 2 so you add 2 closing parentheses before the 1. And then lastly, we imagine there's a 0 here, so we add a closing parentheses here. And yeah, this should solve the problem. So I'll just implement this right now. So I have a variable to store the current depth, and the depth starts at 0. And then I also have a string to store the answer, and I'll put the string in that. I'll put the answer in the end. And then we process the characters one by one. Actually, I'll just do this. And then the depth that we need is just the value of the character. Then we have a few cases here. So if the new depth is greater than the current depth, then that means you need to add more parentheses. And actually I'll change this into a while loop. So while new depth is greater than the current depth, then we'll increase the depth by adding a new character, by adding an opening parentheses to our answer. So we do this. And then there's also a case when the new depth is smaller than the current depth. So in that case, we do pretty much the same thing. Subtract 1 from the depth by adding a closing parentheses. And then after we do that, we also need to add the digit to our answer. So we do that. And then lastly, if we need to pretend that there's a 0 in the end. So if the depth is, while the depth is greater than 0, we'll subtract 1 from the depth by adding a closing parentheses. And this should be it. Yeah, this looks good. Taking a while to judge. I'll just open up the next problem. Okay, cool. Both are right. Okay, so one idea that I have is, so there are two ideas that I have right now actually. First idea is, because we have two colors, we can try to model this as a graph problem where each activity represents a node in the graph, and two activities have an edge between them if those two activities overlap. And then we're basically trying to find a bipartite coloring of the graph, because in a bipartite coloring, you basically color each node with one of two colors, and two nodes which share an edge, which represents two activities which overlap, do not share the same color. So if we can find such a coloring then for this graph, then that basically means that we find a solution. But I'm wondering if there's a greedy solution to this. So given the constraints with n less than or equal to 1,000, I think the bipartite coloring solution will work. But if there's a greedy solution that's simpler, then I'll try it, I guess. So if we yeah, I actually don't see why the greedy solution wouldn't work. I think the greedy solution can even be extended to for more people and not just two. So which one should I write? I think I'll just write the greedy solution, and I'll hope that is correct. In an actual contest, if I see the constraints are this low, then I might actually consider just doing the bipartite coloring solution. So for each activity, we'll represent it with 3 integers. So the input, starting, ending. So the first integer at index 0 is the starting time. The second one is the ending time, and the last integer will just be the index. And we want to store the index because we're going to sort all of the activities by their starting time. And I also have a answer. Okay, so these are, so I can access the characters of the 2 people from doing C of 0 or C of 1. And then we start from the activities with the latest starting time. So kind of like the greedy algorithm for selecting the maximum number of independent ranges. So for this interval, what are the bounds from? Okay, so we'll store an array, means that the array means L means the last starting time a person has. So what we're going to do is we're going to assign activities starting from the right to the left, and then what we'll do is we'll keep track of the latest starting time, and by using the latest the starting time for keeping track of the starting time for each person, we can check if we are, for a new activity, if we're able to assign the person the activity. So for this starting time, if we compare this with the ending time of the new activity, we find out that these 2 activities overlap. So we can't add this new activity to person 1. However, if we compare the ending time of the new activity with the last starting time of the second person, then we realize that we can add this activity to the second person. So, and at the start, we just set it to some really big value to simulate infinity. And then we basically just, we basically just find some person to assign it to. Okay, so we'll keep a Boolean meaning if it's assigned or not. And then if we find out that we're not able to assign it, then we need to return impossible. So let's see. And then we'll return. Okay, actually it's if it's not assigned, okay. And then we'll go through both people. And we'll do it while it's not assigned. Okay, and then we'll try to assign this activity to person J. So actually, I don't think we can do that arbitrarily. So if we have two people such that person 1 has an earlier start time than person 2, then if we have a new activity, it's better to assign this activity. If we can assign this activity to both people, then it's better to assign it to person 1 than to person 2. Because let's say that the starting time is 1, this is 2, this is 3, and this is 4. If we assign this new activity to person 1, then we'll get the starting times of person 1 and person 2 become 1 and 4 respectively. However, if we assign it to person 2, then the starting times become 1 and 3. And it's definitely better to have a later starting time. So in order to have later starting time, which is 4, we should assign it to person 1. Okay, so yeah, I need to process the person with the later starting time first. So do person 1 is equal to 0 and person 2 is equal to 1. And I'll compare these two people with the starting time of person 1 is actually greater than the starting time of person 2. Then I'll actually swap these two. So now person 1 is the one we want to start with, because person 1 has the earlier starting time. So we'll just try person 1. And in order to test that, we'll just compare the ending time of this new activity with the starting time of that person. So if the ending time of this activity, which is stored in index 1 of the activity, if it's less than or equal to the starting time of person 1, that means we can assign this, and we'll give the answer for this activity. So we index the second element in this thing gives the original index of the activity. Then we'll set it to the character of that person. Okay, and then we do person 2. So if we haven't assigned yet, and it's possible to assign it to person 2, then we'll assign it to person 2, and we'll also just set the answer. Also, I forgot to update the starting time. So the latest starting time of person 1 becomes the starting time of the new activity, and the latest starting time of person 2 in this case becomes the starting time of this activity. Yeah, that should be it. So lastly, if we didn't return impossible in the process, then that means we'll just output the answer. And hopefully this should work. L was not yeah, I forgot to declare L. Now my answer for case 1 is slightly different, but there can be multiple possible solutions to this problem. So I'll just check to make sure that it works. So yeah, it works. Okay. So I'll submit this right now. And by the way, this solution works in nlogn time. So it works for much bigger constraints. That's why I chose to write this solution instead of the bipartite matching solution, because it's more educational for this, which is the point of this video. And hopefully it actually works. Really cool, I got it correct. Okay, so yeah, move on to the next problem. Okay, interesting interactive problem. Hidden verdict. Oh no. So B can be up to 100. And we have 150 queries. Okay. I think because like after the first query, everything basically just switches. So maybe the first query is useless. I'm not sure. But for now I don't see any use for the first query. So okay. B is even. Like B is even, which is kind of important because if B is even, then that means if B is odd, then there'll be a middle element which doesn't move, but that's not the case. So is there some possible way to So after like each fluctuation happens, you probably want to test some of the bits you already tested before to figure out which four of these exactly happened. So we have kind of makes sense. So if this is an entire array, then the first thing I probably want to query these two bits. And let's say these are both different. Maybe they're 0, 1. Then if I see that, and if I see that after some query, these two changes, so maybe it becomes 1, 0, then that means that exactly one of the two things happens. And if they stay the same, then either nothing happened or either both of the things happened. Because the reason both of the things can happen is because if we do the complement first, so change 0 into 1 and 1 to 0, and then we also do a reversal, so then becomes 0, 1. So that's why it'll look the same. So if we query a pair of numbers which are different, then we're able to distinguish between these two groups. Okay, so let's say that we find a pair of elements which are the same, so like this 0 and this 0. Then if the array becomes reversed, then these two don't change. But if we apply the complement to this pair, then these both should become 1, 1. So by looking at the state of one of these two pairs, we can tell if the array is complemented, if the array has been complemented or not. So okay, so if we find a pair which is different and a pair which is the same, then after each time something weird happens, after each time a quantum fluctuation happens, we just need to query two bits, and then we can find out exactly which one of these four happened. So I think the general strategy is probably like this. So basically, I think I'll just ignore the first query, and then I'll ignore the first query, and then for the group of queries from 2 to 10, from 2 to 11, what I'll do is I'll just query the 5 here and the 5 here, and then stuff will change. And then this is for queries 2 to 10. So I'll make, so query 1, I don't know what to do with query 1. It's kind of useless, I think. And then queries 2 to 10, 2 to 11, I'll query these 5. And then after query 11, something changes. And queries 12 and 13 will be used to detect what changes. So if I find a pair which is different and a pair which is the same, then I can basically just find out how the entire array changes. And then using that, I can basically just change the array to obtain the updated array. And after that, I basically have the updated array. So from 14 to 21, I'll basically query the next 4 bits. And then after 21, the array changes again. But that's not a problem since I just need to query 2 bits and then just need to query these 2 bits. And then I can know exactly what changes. And then I'll just continue with the next 4 pairs. Actually, I don't even need to, wait, yeah, I get the next 4 pairs. Okay. So now here comes a tricky case. And you might be thinking like, what if we don't find both of these pairs? What if we only have a pair which is the same, or we only have pairs which are different? And for that case, it actually is even better for us because we only have to query we only have one type of pair we need to query. So, because if all of our pairs are, for example, if all of our pairs are basically the same type, then we don't have a different pair to check whether or not to distinguish between these 2 groups. And we can only tell if a complementation happened. But it only matters to us if a complementation happens. We don't care if the array is reversed or not, because if the array is reversed, then it doesn't change the bits that we know so far. So we just need to check one pair. We just need to check if a complementation happens. Okay, so I guess this is the general strategy of what my program is going to do. And, oh yeah, and then I basically do this thing until I find a pair which is different. A pair which is different. Like this pair. So yeah, so I'll just, number of bits is 100 and I have 150 queries. Seems like I have enough queries. So how many times will this happen? So the first query is wasted, and the second query we can find 10 of the bits. So let me just do some quick calculations. So after the first group of queries, each time we can figure out 8 bits. So that means we need a total of 12 times. And so that means we end somewhere at like we end somewhere at like 130 something queries. So it should be fine. Okay. So now I'll implement the solution. And this doesn't seem to be that hard of an interactive problem, so I'm not going to bother using the local testing tool. Okay, so for D, I'll just T and then see what's the input. Initially T and B. Note that B is the same for each test case. Okay. Then I have B here. Okay, so how do I solve this? Okay, I'll create a query function, and which query some bit, yeah. And I use 0 indexing, so I need to add 1. How does it work? Print 1. Yes. Okay, and then here's an answer. We input the answer, and then we return the answer. Return the bit. Okay. So for the first query, we just waste it. So waste first query since it's useless to us. And then we use the next 10 queries to find 5 pairs. So, okay, so I'll do this. And then I'll create a function for finding the pairs. So call this find pair I. And I should store an array which represents the answer that I have so far. Okay. Find pair, and this tries to find the pair for I and B, 1 minus 1 minus I. So these two form a pair. So yeah, this is pretty simple. I just set the array at index I to the value of the query. And I do the same for the other element. Okay, and now I find the pair. Oh, and I need to keep track of if I found the pair which is the same and the pair which is different. Okay. So at the start, I'll have same pair is equal to -1 and different pair is equal to -1. And I need to declare these. Okay, so after I find each pair, I need to update same pair and diff pair if they have not been found yet. So if same pair is equal to -1 and this pair has the same value, then I'll set same pair equal to the current pair. Okay, and I'll also do the same thing for different pair. Okay. So now we find the first 5 pairs. Yeah, okay, so it'll be fine. And after that, the array will change in some way. Okay, so keep track of integer c. Okay, c will mean how many pairs we have found so far. So c starts at 0, and we find the first 5 pairs using this loop. Okay, and then what we do is after we do these 11 queries, the array is going to change in some way. So okay, so we'll have let's call this find change. So it'll find what the change that happened that happened, one of the 4 changes. Okay, so void find change. So remember the first thing we do is wait. Okay, by checking the same pair, we can find if a complementation happened. So let's keep a boolean thing. So it means if a complementation happened or not. Okay, so in order to do that, if we actually found a pair which is the same, so it's not -1, and we'll query that same pair. So same pair is, but it's not equal to its old value. If it's not equal to its old value, then that means a complementation happened. So we set complementation to true. Okay, so now we check the diff pair. So to find if we did a reverse. So if diff pair is not equal to -1, and Okay, so you have to consider the cases here. So if the different pair changed, then as I said earlier, if it changed, then exactly one of these two things happened. But if it did not change, that means that either both happened or none of them happened. So if it didn't change, then that means both happened or none of them happened. So that means the status of reverse should be the same as if a complementation happened or not. Okay, so but if it did change, then that means exactly one of them happened. So these two have to be different from each other. So if it changed, then that means we set it to the negation. We set it to be different. Okay, and then lastly, we found out if a complementation happened and if a reverse happened. And now we just need to perform the changes on our array. So if a complementation happened, then for each of the elements, I'll just make them their complement. And if a reverse happened, then I'll just reverse the entire array. Okay, and this should properly find the change. Okay, so now wait. So while C is less than B divided by 2, so while we haven't found all pairs yet, what we need to do is we test 4 pairs. So at most 4 pairs, so I just wanted them 4. And we also need to make sure that C is still less than B divided by 2. So we need to make sure that we haven't found all pairs yet. We add 1, and we find pair. Okay, and then after these 4 cases, actually I make I put I over here so I can check if all 4 have happened. So if I is equal to 4, then that means all 4 happened, and that means a change happened, and we need to find the change. So we call find change again. Okay, so this should be good, right? So after we output the entire thing. Okay, so we just output the array. Yeah. And then we read and answer to see if we are correct or not. Okay, so chart okay, and cin okay. And then if it's not if okay is equal to no, then let's just exit. And this should probably be good. I'm actually too lazy to test this thing, so I'll just submit it and hope that works. Turns out that I read the problem wrong. Wait, I actually thought it was after the response was given. That means I don't need to find change over here. But I think it should, yeah, it should still be fine. I just need to find change over here, okay. That should be good, okay.